Hello there. In this video we're going to be practicing the circle theorems involving segment lengths of chords and secants. So in this one over here I have two intersecting chords, and I got that intersection point there. Now the nice thing about all these problems is it has to do with the distance from the intersection point P to where the circle is. So that distance is 4. That distance is 5, and that product has to equal this distance here times the distance over there from where P meets the circle, x. And then we can divide and solve for x, and we get 20/3, which is about, what is that? That's like 6 1/3, 2/3, 2/3, yeah. Now, in this video we're not going to be unlike the other one where I teased at the end, we're not going to be doing the proof for why this works. There are similar triangles involved. We'll do that in a different video, but it's just that distance to the circle, that distance to the circle, their product, and then the other chord, distance to the circle, distance to the circle. And that gets repeated in all of these, even when it's outside the circle. So this point, that's the intersection point P, distance to the circle. This is the near, 6. And we're going to multiply that by the whole, and the whole is not 7, the whole is 13 in that case. That's that total length. And that's got to equal the near on this side, which is 5, times the whole thing here, which is 5 plus x. Alright, so now we can multiply through, do a little bit of subtraction, and finally divide, solve for x. 53/5, or that could be written as, decimal's okay on this one because it is a precise number. Okay, next one. There's a couple different ways to do this one. So you could actually set up a right triangle in here and say that x squared plus 2x squared equals the radius. So this is the Pythagorean theorem approach for it, and we'd have to expand that out. But I also want to talk about another option, which would be to use the circle, the chord theorems. So that's the center of the circle. This actually extends down here, and that length there is x plus 3. So now when we view this as a point, if that's 2x, that over there is 2x because it's this is a line going through the center, and we know that it's perpendicular, so it must be bisecting that length. And then we can say that the distance from here to here times the distance from here to here, which is the same, that has to equal the distance on the top, which is 3, times the distance down to the bottom. Okay, this may look a little bit garbled here, but it's this length here, which is 3, times this whole length here, which is x plus 3. So adding those together, I get 2x, multiply the 3 through, I get this. Now this line here and this line here, once you would gather like terms, actually you could cancel out those x squareds. You can kind of see that there. Those would cancel. And you get the same thing. So it doesn't really matter which approach you take. You should wind up with the same quadratic and be solving the same quadratic. So set that one equal to 0, and then start, well, lots of different options. I'm not sure that this one factors. I don't think it does. Let's just do the quadratic formula. So there's step 1. Whoops, actually I have a mistake in there. That should be a 4 inside there. Boom, multiplies together to be 8. Okay, so scan that. I'm getting a negative times a negative, so I know that it's going to be plus. And this is 4 times 4 times 9, 16 times 9, that's pretty big. But 9 is also 3 times 3. So 4 times 3 times 4 times 3, that's 12 times 12, that's 144. And quadratic formula problems always take up more space. So one useful thing to adding those together to get 180. One useful thing to know about 180 is that 5 36s are going to fit in there. Something to do with pentagons. So then the square root of 36 becomes just 6, and we see that we have a bunch of even numbers there, so there's going to be 3. Now this plus minus, it's a length, so it's going to have to be the positive version. 3 plus 3 root 5 all over 4, and that'll be final answer in simplest radical form. So a lot of these problems, remember, was just an application of that circle theorem thing. Now, we didn't even go in here and actually observe or sketch in where the similar triangles were. We were using that ratio of point to the circle, that times that equals that times that times the whole equals that times the whole, that times that equals that times that. This one got a little bit longer because of the quadratic formula. Thanks for watching. Character and Scholarship for Life.